Okay, so let's dive in. You sent us these sources, a whole stack actually, on geometric shapes.
Yeah, and they seem to really, zero in on triangles quite a bit.
They do. So our mission for this deep dive is to really pull out what these sources say about congruency and only what's in this material you gave us.
Right. And the sources, well, they define congruency pretty clearly near the start. It's about geometric figures being essentially perfect copies.
Perfect copies.
Yeah, like if you could physically pick one up and put it right on top of the other, they'd line up exactly. Everyone.
Okay.
The text mentions this for simple things like two lines of the same length or more complex shapes like polygons where all the matching bits fit perfectly.
Got it. Perfect copies. And yeah, like you said, the material really focuses this idea onto triangles.
Exactly. So when your sources talk about, say, triangle ABC and triangle DEF being congruent, they mean every part lines up.
Yeah.
Every side, every angle in ABC has a sort of perfect match in the same spot in DEF.
Ah, and that's where that symbol comes in, the one that looks like an equal sign with a squiggle.
Precisely. That little symbol, equiv or forgive, sometimes a Kong, just means is congruent to. It's the shorthand.
Okay.
And, this leads to a really powerful idea right off the bat. The sources emphasize that if you know two triangles are congruent,
Yeah.
then their corresponding parts, the matching sides and angles have to be equal.
Yeah.
So side AB matches up with side DE, they must be the same length.
Right.
And angle A corresponds to angle D, so they have to be equal. Same for all the other pairs.
Wow. Okay. So knowing they're congruent unlocks all that information, that all 6 pairs of parts match. That feels like a huge shortcut.
It is, and that's the perfect lead-in to the next big thing from your sources.
There's...
You don't actually need to check all 6 pairs to prove they're congruent.
Ah, right. There are tests, conditions.
Exactly. Clever little minimum requirements. Your sources lay out 5 key conditions.
Okay, let's hear them. What are these tests?
First up, SSS, side, side, side. Pretty straightforward. If you can show the 3 sides of one triangle are equal to the 3 corresponding sides of the other.
Then they have to be congruent.
They have to be. The sides lock everything in place.
Makes sense. What's next?
Then there's SAS side, angle side. Now this one's specific. It requires 2 sides and the angle between them.
The included angle.
Exactly. The included angle has to be the one formed by those 2 sides. If those 3 parts match in both triangles, like in that figure showing ABC and ZXY, then they're congruent. The position of the angle is key.
Okay, so the angle has to be sandwiched between the sides for SAS. Got it. What about ASA?
Angle, side angle. Similar idea, but flipped. Here you need 2 angles and the side between their vertices.
The included side.
Right, the side that connects the 2 angles you're looking at, like side BC between angles B and C in that other figure. If those 2 angles and that specific included side match up.
Congruent again. Okay, so SS needs the included angle. ASA needs the included side. What if the side isn't included?
Good question. That brings us to AS. Angle, angle, side. This one works too. If you have 2 angles and a side that's not between them, and those corresponding parts match in the other triangle, they are also congruent. Your source shows this, comparing angles B and C and side AC with angles Q and R and side PR. See, AC isn't between B and C. Still works.
Huh. Interesting that a non-included side is okay there. And wasn't there one more? Something specific.
Yes, RHS.
Yeah.
Right angle, hypotenuse side. Now this one is only for right angle triangles.
Only for right triangle, though.
If you know the hypotenuse, that longest side opposite the right angle and one other corresponding side are equal in 2 right triangles, they're congruent. That figure with ABC and FES shows this.
So SSS, SSASA, ASS, and RHS, those are the 5 ways from the sources to prove congruency. But they also mention something that doesn't work, right?
Oh, absolutely crucial. Yes. AA, angle, angle, angle. That is not a test for congruency.
Why not? If all the angles match.
Because, well, if all the angles match, the triangles will have the exact same shape. They'll be similar, but they won't necessarily be the same size.
Ah, okay. Like a small photo and a big poster of the same photo. Same angles, different sizes.
Exactly that. Think of a tiny equilateral triangle and a huge one. All angles are 60 degrees in both, but they're definitely not congruent. You need at least one side measurement to fix the overall size.
Right, the side locks in the scale. Okay, that makes perfect sense. Can we quickly run through one of the examples, like example 3?
Sure. So in that one, you're given that line AB is parallel to line CD.
Okay.
And you're also told that the length of AB is actually equal to the length of CD.
Right, parallel and equal. And the goal is to prove triangle AOB is congruent to triangle DOC.
Exactly. So look at the figure. Because AB is parallel to CD, we know something about the angles. those Z's angles.
Alternate interior angles.
You got it. So angle BAO must be equal to angle CDO. That's one pair of angles.
Okay.
And for the same reason, angle ABO must be equal to angle DCO. That's the second pair of angles.
And we were given that side AB equals side CD.
Correct. Now look at where that side is. Side AB is between angle BAO and angle ABO.
Yeah.
And side ZD is between angle CDO and angle DCO.
So we have angle, side, angle.
Exactly. ASA. We've matched an angle, the side included between them, and another angle.
Which means by the ASA condition.
Triangle AOB must be congruent to triangle DOC.
And because they're congruent, now we know all the other parts match up too. Like AO must equal DO and BO must equal CO.
Precisely. That's the power. You prove congruency with one of the shortcuts, and boom, you know all corresponding parts are equal. It's efficient.
Yeah, really efficient. Okay, so wrapping this deep dive, congruency means they're perfect copies, exact duplicates.
Right. Same shape, same size.
And your sources give us these 5 powerful tests, SSS, SS, ASA, ASS, and RHS for right triangles to prove it without measuring everything.
But crucially, not AAA.
Right. AAA gives you similar shape, but doesn't guarantee the same size. That's the key distinction.
Right. And understanding these rules, these conditions, it's just fundamental for tackling geometry problems.
Yeah.
It lets you deduce things instead of measuring them.
Absolutely. So here's a final thought for you, building on this. Why do you think knowing just the 3 side lengths, SSS, completely fixes a triangle size and shape, guaranteeing congruency? But knowing just the 3 angles, AAA, leaves the size completely open, something to ponder about the power of those side lengths.